On 14.4.
Yeah.
Yeah, especially on, not this one.
It's hard.
Number 5 is very long.
Question number 5?
Question number 5 is very long. Be prepared. I feel like it was. I feel like they made it harder than they made. So all the problems in my math lab are tied to a textbook problem, and the textbook problem that they tie number 5 to, which is number 33 in the textbook, is immensely easier than this one. And I feel like they probably made a typo when they were doing it. The answer is that I checked the answer to make sure that it was right. The answer that they have is right and everything. But if you look in the textbook, they have a plus between the x and the y part in this first component. So then when you do the curl, it's way easier. When you do g sub x minus f sub y, it's much, much easier. But because this is a product, it's going to lead to a couple of integrals that are going to involve integration by parts. And so it's going to be a long, this one is going to take you more time than any other problem in that homework. So just be, if you know that it's coming, you can do it. It's just a couple of integration by parts. There's an x squared times sine, depending on the iteration that you get. There might be an x times cosine of 2x. So just be aware that when you do this, so first off it says to use Green's theorem. And it's saying use Green's theorem to evaluate the line integral. So the implication there is to use the double integral. So it kind of depends on what they give you. If they say use Green's theorem to evaluate a double integral, they're kind of implying to use the single integral. If they say you use Green's theorem to evaluate a single integral, they're kind of implying to use the double integral. And both of them will give you the right answer. So here it's saying use Green's theorem to evaluate the single integral. So it's kind of implying to use the double integral of the curl. Obviously, you could do this directly and parameterize this region, but it would be two curves because this region is comprised of the sine part, and then it's also comprised of this flat boundary at the bottom. So if you did do it directly, which is that's going to take you even longer. I would probably not recommend doing that unless you're really bored. So you would want to use the double integral of the curl, and the two-dimensional curl is g sub x minus f sub y. And so you're going to do this over the region. So over that region, this is your R. So just be aware, as you g sub x minus f sub y, it's going to be it's going to be a little messy when you go to integrate it because you have to use integration by parts. So try that out. Yeah.
So you won't have to convert to polar, correct? Because
No.
they give you those bounds.
Right.
Okay.
Yeah, you won't have to. You won't have to convert to polar. But as you do this and you integrate with respect to x, most likely you're going to integrate with respect to y first. You're going to most likely do a vertical element. Most likely, I would recommend that. Horizontal element would be a pain in the neck. So if you do this, you would end up doing it dy dx. And when you integrate with respect to y, that's what's going to lead you to these products with x's. You're going to get x squared times sine x, or x times cosine 2x, something like that. So you'll have to use integration by parts. I did a couple of iterations. Once I had to do integration by parts twice. Once I had to do power reduction followed by integration by parts. I had to do it twice that time also. So probably 2 integration by parts. I feel like I did it once where there was only 1 integration by parts also. It just depends on some of the numbers. Okay, so try that. Now, this one's a lot easier. I'm not sure what the question was on this one. Just
like everything?
Everything!
Yeah, like, I guess.
Everything is 0 with a twist in it.
It was weird, like it had us.
Right? Wasn't that our quote on the test this time? Kurt Vonnegut quote?
Huh?
Oh, no, that was.
I thought this one was different.
It was a different test.
Because it had us do like
Different.
separate.
Different test. So, okay, let's talk about this. So first off, divergence. We partially differentiate our vector field, each component in order, with respect to x, with respect to y, add them together. So the divergence of this vector field is going to be partial of first component with respect to x, partial of second with respect to y. So the divergence here is 0. So this makes the double integral side of Green's theorem really easy.
0.
Because the double integral of 0
It makes you do it both ways.
dA
That's why.
over R is going to be 0. So that's the easy
Is
way.
this from the book?
Yeah.
Yeah, they make you do it with the parameterization.
Yeah, that's the second part.
Okay.
Yeah.
The parameterization was the hardest part of that one.
Okay, all right, let's talk about, was that your issue also, parameterizing? So there's a lot of parameterizations you could use. So if you look at the shape here, you do not have to parameterize both on the same exact interval, if you know what I mean. So 16 minus x squared is going to look something like that. And then we have the boundary here. So I believe the way that they show in the examples, they parameterize the line segment from -4 to 4. Now, you don't have to do that. You could parameterize, anytime we parameterize line segments, we usually go 0 to 1 and use the whole distance between the 2 points as our vector, as our sort of step. But you could also parameterize that -4 to 4. But you do not have to parameterize both the upside down parabola and that line segment on the same interval. Grant.
The way that the example problem did,
Yep.
which made it way easier, was just to have the parameter, or rather have the equation be t comma 0,
Yep.
and have time from -4 to 4.
-4 to 4. Totally fine. Yep. Does everyone follow that that would be one parameterization for the line segment part? So we want to go counterclockwise here. So that is definitely one way that you can parameterize this. Let's call that C1. So C1, parameterize R of t equals t comma 0, and then t would go -4 to 4. Totally fine. You could also go 0 to 1, but then you would do 4 minus 4, you would get 8t and go 0 to 1. Everyone follow that? So you could do, or you could do, no, that's not right. It's 8t. It's 8t minus 4. I forgot to subtract off the initial point. So 8t minus 4. This would be the way that we have historically done it. And if you plug in 0, you're at -4. You plug in 1, you're at 4. So that would also work. Doesn't matter. Either way. Totally fine. The way it comes out in the wash is that you have to plug your parameterization into your function, into your field. So you would create a field with these two or a field with those two. Does not matter. So parameterizing the parabola. That's the next thing. So if we want to parameterize it correctly going counterclockwise, fine. We could also parameterize it clockwise, but then multiply by -1 in the end. It's not going to matter. So let's try to parameterize it the way they have it there. So parameterizing for the parabola, we're going to do R of t is equal to, so this is a function. Functions are easy to parameterize. You could definitely do this. That's how we typically parameterize a function. Let x be t and let y be f of t. That's typically what we do. But if we do that, what happens? Does it work? If we let t go from, what happens if we let t go from -4 to 4?
Yeah, pretty much. We kind of overlap with C1. Is that your problem?
Well, if we plug in -4, if we do the -4 to 4 thing, if we plug in -4, we're here first, right? This would be the t equals 0, or the first endpoint. And then plugging in 0, we'd be at 0 coming. So we'd be going clockwise instead of counterclockwise.
That's okay.
And that's fine, because then you can just multiply by -1. Totally works. Or you could do another parameterization. Let me move it over somewhere else out of the way. Let's go above it. Another type of parameterization that we could do is we could go R of t equals, and I think this is what they do. I think they do probably -t. -t, comma 16 minus t squared. All right, so then when you plug in -4, you're at 4. And when you plug in 0, you're where you should be. And when you plug in 4, you're at -4, comma 0. So either one of those will work. This one you have to multiply by -1 in the end because you went clockwise instead of counterclockwise. So either of those will work. So see if you can get the second part then. Take the derivative, whichever parameterizations you use, take the derivative, do the dot product, and integrate. Yeah?
So pretty much the second one, you can go from 4 to -4?
Yes, exactly. When you say second one, do you mean this one?
No, the one you wrote second.
Up there?
Yeah.
That one will go -4 to 4. Right? Because if you plug in -4, if you plug in -4 right there, you're at 4. And if you plug in 4, you're at -4. So if you use this one, you're just going to go regular -4 to 4 and not switch anything.
Okay.
This one, you could multiply by -1, or you could go 4 to -4 for this one, for the one that's written underneath. Yeah.
What would be like the next step for this problem? Like if we were doing it the harder way?
Yep.
So we would integrate them separately?
So do them separately,
So
and then just
do
add the two
the
results together.
T0 and then the one for the parabola and then add the results together?
Yeah. Because for a line integral, we're dealing with piecewise smooth curves, so it's basically the line integral on each of the separate smooth parts.
Okay.
So we would figure out the line integral on that, we'd figure out the line integral on that, and then add them together. Now, if you happen to have limits that match, you could combine them into one integral. But in general, you don't. In general, that's not going to be an option. Usually, you aren't going to be so lucky that you could combine them into one integral.
So with this one, it's just coincidence? Or?
It's a coincidence, yeah. So if you had a regular shape that was somewhere off in the xy plane and wasn't set up so nicely, you wouldn't have the same limits. Like a lot of people would parameterize this line segment like that way and go 0 to 1. And so now remember that with the flux form of Green's theorem, when we take the derivative, so let's write this out because this is the part that gets confusing. Bless you. So let's look at both again. Just it can't hurt to write these things down a lot. So the circulation form is the integral of f. The book will write it f dot TDS, but we never evaluate it that way. We never find capital T, and we never parameterize according to S. So the way that we generally deal with the circulation form is rewrite it as FDR. That still is not really in a form that we can evaluate nicely, and so the evaluation form of this integral is f dot r prime times dt. So that's the evaluation. This is what we typically are using to do our calculation. So that's for the circulation. Now this one's asking for flux. So the flux one is going to look a little different. So here we're adding up the normal components of the vector field. And the book doesn't give you a shortcut version of this, but the way that we've been writing it as our sort of shortcut, not standard notational form, is to have the perp put into the r prime part. So it's f dot r prime perp, with the understanding that we are switching the sign on the first or second component? Second component. So if we are looking up here at the circulation one, your dr is dx comma dy, but down here with this one, that dr perp is going to be dy comma minus dx. So, but these are the two evaluations. These are the two evaluation methods that we use. Those are the two. So, circulation, just r prime. Flux, r prime perpendicular, where we switch the second sign. And so for each of these, whatever parameterizations we use, we take r prime, switch the coordinates, change the second sign. Yeah.
So something that kept confusing me when I was doing this homework was when it says it's dy negative dx, is that the y and the x of the vector field function, or is that
So
of the
when we
radius function, or what?
when we are looking, say, right here, right there, you can look at your vector field with x's and y's, and you could take, and it's that strange form that we usually don't write it in. So we could write this as minus 4y dx plus 4x dy. But we usually don't do that because most of the time we can't evaluate it because the letters aren't lined up. Like if you had a vector field that was super, are there no markers in this classroom?
You can have a pink one.
Oh, ooh. Thank you. If you had a vector field that was lined up so nicely that you had just x's here and just y's in the second component, then when you do your FDR, here you could get away with doing x squared dx plus y cubed dy because these are all lined up perfectly, x's with x, y's with y. So you could get away with it there. Most of the time, that's not going to work. So what we do is parameterize the curve with a t, take whatever the parameterization is and plug it into f so that f is now a function of t's. It's a field with t instead of x's and y's. And then we have just a single integral with just t.
Okay.
So this dy and this dx is, you can think of it as differentials from the vector field variables. So if the vector field has x's and y's, those are the vector field differentials.
Okay.
It's easier to go to t, though. It's going to be easier to go to t.
It was just kind of hard to keep it all track because there's so many x's and y's, and like they all go different directions.
I know. And sometimes we have f comma g, and sometimes we have g.
Yeah, and like is this the x and the y of f, or is this the x and the y of g, or is this the x and the y of h?
Well, and like when we do flux here, when we do flux,
Everywhere.
we do this one with respect to x, this one with respect to y. But when we do curl, we do this one with respect to x and this one with respect to y, and we subtract instead of add.
Okay, so just practice basically.
Yeah. Yeah. Excellent. Excellent. Okay, so let's see. Any other questions on either of those? Yeah.
That parameterization that the 18 minus 4 on the last one,
Uh-huh.
where did that come from? Did you just do like the negative 4, 0 and 4, 0 and use those to build that?
This parameterization here?
Yeah.
That one right there?
Yeah.
Yes, so I did it with the standard way where we do the difference.
Okay.
We do terminal point minus initial point. So 4 comma 0 minus negative 4 comma 0, so we would get 8 comma 0.
Okay.
Multiply by t,
Right.
and then add the starting point,
Okay.
negative 4 comma 0. So that's sort of the way that we traditionally have parameterized line segments.
Okay.
Here you can get away with doing it this other way. It's really intuitive because it's on the x-axis. Y is always 0. So you can. It's a little sneaky. You can do it with a slightly easier method. All right. So, and then that one we talked about, number 5. So let's go ahead and get started on 14.6. 14.6 is probably, some people feel like it's the hardest section in this chapter. I don't feel like it's the hardest section in this chapter, but some people feel like it is. It's very analogous to what we already did with line integrals. The only difference now is that we're going to do surface integrals. And you guys tell me, we had 2 types of line integrals. If we were integrating a function, did we multiply by r prime or the length of r prime? Length of r prime. And let's just, we'll make that a t. And if we were doing a field, we multiplied by r prime or the length of r prime?
R prime.
R prime. Okay? So same thing here in this section. It's just that we're going to be integrating on a surface instead of on an interval.
So 3 dimensions.
3 dimensions. So our domain is now a surface. And we can either have a regular function defined on the surface. So we've got our surface, and every point on the surface has a number tied to it. Maybe it's the temperature of the surface at that point. Maybe it's the density of the surface at that point. Maybe it's some other random generated. Maybe it's the height of the surface at that point, whatever it is. So now our domain is the surface. So we've got our surface, and at every point on the surface, there's a number. And a surface integral is adding up all those numbers. That's what integrals do. Integrals add up a bunch of numbers, and those numbers are coming from something. Function height, function value, whatever it is. We could also have as our function a field instead of a regular function. So at every point along the surface, instead of thinking of a little number being tied to it like we do with this integral on a line or on a curve, now we have a vector that's on the surface at every point. So we have a choice. Just like we had with this Green's theorem thing, we had a choice. Here we added up all the tangential components. Here we added up all the normal components. And so these integrals look slightly different. We took r prime or we took the r prime perp. So when we integrate a field, we have one extra degree of freedom. We have to decide which component of the field are we adding up. If we have our surface, are we going to add up all the normal components of the field? We could do that. That's going to be called flux. Or are we going to add up all the tangential components of the field? We can do that. That's going to be, we called it circulation back here. And in 3 dimensions, we'll call it Stokes Theorem. But it's the same idea. So surface integrals are just Green's theorem with circulation and flux, but we're on a surface instead of being on a curve, which translates to an interval. So our domain is 2-dimensional instead of 1-dimensional. Right, if we integrate along a curve, the domain is 1-dimensional. We just have a t. If we're on a surface, our domain is 2-dimensional. So we're going to have a u and a v. All right, so let's first talk about how we parameterize surfaces. This is the part that blows most people's minds, is how do you come up with the parameterization? And we'll do a few of these. It's the only way to generate parameterizations for surfaces is with practice. It's much harder than with curves. With curves, it's easy for the most part. We've done ellipses, we've done circles, we've done lines. Curves are pretty easy to do. You know, a little bit of thinking about the radius of the circle. Oh, that goes in front of cosine and sine. If you have an ellipse, you just modify the coefficients so that they're not the same. Surface is a little bit harder. We'll talk about some strategy. So a surface, it's 2-dimensional. So we're going to have 2 parameters, a u and a v. So the parameterization of a surface is going to have an x, a y, and a z, because we're in 3-dimensional space. And we have 2 degrees of freedom. And we're going to use u and v to represent those 2 possible degrees of freedom. Sort of analogous to when we're dealing with the parameterization of a curve, we only have 1 degree of freedom. We just have a t, and that moves us along the curve. So it's that same kind of idea. So for the surface, we have our parameter plane. So we have our parameter plane where the u's and the v's live. They may or may not tie to something in the xy plane. The parameter plane may have nothing to do with the xy plane, or it may be lined up nice and geometrically so that you can say, oh, this, there could be some geometric relationship. Not necessarily the case, though. So we've got our parameter plane, u and v, and we've got our surface. So the idea is that we're building a function. So this is a vector-valued function. Every point here in the parameter plane is going to correspond to 1 point on the surface. So if you plug in the coordinates of u and v here, you plug them in up here, here, and here, and you get this, you get your whatever is called an ordered triple. And it puts you up there on the surface. So every ordered pair u comma v generates an ordered triple on the surface x, y, z. Same as it ever was. Domain, range. So here we go. Okay. So we have a cone, and we want to find the parameterization for the cone. So the very first thing in your mind whenever you're parameterizing a surface is, okay, I need a u and I need a v. We have to decide. Quite frequently, one of those variables is going to be very simple. Like when we look up here at this cone equation and we look over at z, z is very simple. It's just going 0 to 4. So there's always going to be one of the u's or the v's that most likely is going to be pretty simple. And you sort of start with that as your anchor, and then you build up to the other components. So let's let's set up the structure first. So we know that it's a function of two variables. It's a vector-valued function of two variables. It's a vector function. We know there's going to be three components. Give myself lots of space. And I see up here that z is going to go 0 to 4. So I'm just going to say, let's let v be z and see what happens. So I'm going to, u and v are both going to have some sort of domain. And if I do that, v is now designated to go from 0 to 4. It's representing z. And so what I'm hoping then is that I can represent the x and the y components with just the u. So let's see what happens here. Quite frequently, when you have x squared plus y squared, you think polar. You think, is there a way to somehow use polar coordinates? And let's think about that for a second. If we let z squared equal 4r squared, if I solve this for r, and I know you're going to ask me, why would I solve for r? I'll answer that in just a second. So if we solve for r, and r we're going to choose to be positive, or imagine everything is positive. R is going to emanate in the positive direction from the origin.
Although actually, I don't know, is it just me or
Yes.
I'm wondering if it can be negative.
No, not in this case. Not in this case. When we're in spherical or in cylindrical, r is always designated to be non-negative, and rho is always designated to be non-negative. Right? So what I've done here, this equation, when I let x squared plus y squared equal r, it's just giving me a relationship between r and z. And r is what it always is in polar. It's emanating from the origin, going out radially. And so, let's see what we can do here. What we have to build is this equation, and we have to somehow, we can't use r because that's a polar thing, so we want to use a u. And can you see what we would want to do here? If we let, maybe if we think about cross sections of the cone, aren't the cross sections of all the cone, aren't the cross sections of the cone circles?
And two
Yes.
triangles.
And two triangles. If we do horizontal cross, if we have a cone that opens up, cross sections are all circles.
But if you cross it like that.
No, that's not. No, the cross section, we're crossing. When we say cross section, we're
You mean horizontal?
I mean horizontal cross
Okay.
section. Yeah, I guess you could. Yeah, horizontal cross section. Because we're thinking of it as a function, like the upper part of the cone or whatever. Think of it as a function. So cross sections are circles, and the radius of each of those circles is related to the height. That's how the radius of each circle is related to the height. So z I let be v. So let me just write this down and then we'll talk about it. So cosine of u. If I have a circle, I'm thinking r cosine u, r sine u. So let's just take a look at that. So if we wrote a very simple equation, if we wrote something like a parametrization, if we just think about, like if we think about 3 cosine of t comma 3 sine of t, we all know that's a circle of radius 3, correct? And so all I'm doing is taking the radius and saying, well, we need to have different radii. Because if we think about the horizontal cross sections, the circles are getting larger as you go up the z-axis. But the radius of the circles depend on the height. Right? Like if you have a cone that is at 45 degrees, we have that cone right there, we know that z and r are equal if it's at 45 degree cone. Z and r are equal. So the radius is a function of the z value. And that's why I did this here. I said, okay, well, if we think polar and solve for r, the radius is related to the z value in this way. And then instead of r cosine and r sine, we're going to put that in there. All right? Yes, I know, it's hard. Okay. So Does that make some sense?
Sure.
Yeah, some sense. All right.
We're
So
using R and theta accepted some
U and V. So the U is going to play the role of rolling us all the way around, and V is playing the role of taking us up or down. So V is measuring height. That's the Z value. And then the corresponding X and Y are going to depend on whatever that height is.
Question.
Yeah, go for it.
Is that always the case? Like the U is always just going to be rotational, and the V is always going to be a
It's your choice.
Okay.
I mean, usually most of us will do U as the angle. But it's your choice. You can let U be the height and V be the angle. It's not going to matter. Usually we'll do U as the angle.
Just make it harder to grade, right?
Yeah, exactly. There's always so many. All right, let's try another one. This one's probably easier in some ways. So here we have a cylinder.
Hold on, there's a question.
Oh, question.
Yeah. What if the cone is not a 45-degree cone?
Then you're going to have, then you have some tilted relationship, like this one is not at 45 degrees. So here, there R is exactly equal to Z, but here R is equal to Z over 2. So if our cone is steeper or less steep, then the relationship between R and Z will just be different. So we figure out what the relationship between R and Z is by letting R squared equal X squared plus Y squared. All right, so let's try a cylinder. All right, so this cylinder, there's no X in it, so we know that it's pulled in the X direction. All right, so R of U comma V, so there's no X in there. That is going to be like the easy variable. There's no X in there, they just tell us X goes 0 to 9. So let's let that be, what do you want to let that be?
U.
Okay, so U, so that means you're saying we're going to use V for the angle this time. So let's see. So this in the YZ plane, we have a circle of radius 6. So we're going to go 6 cosine V, 6 sine V.
That's it?
That's it.
and
And then we have to tell us, then we have to indicate that U is going to come from the interval 0 to 9, and V is going to come from the interval 0 to 2 pi. So here we use V as the angle. You told me to use U first, so it doesn't matter though. Yeah.
I spaced out for like 2 seconds when you did the 6 cosine V, 6 sine V. Where'd you get those?
So this is a circle of radius 6.
Certainly.
Circly.
Circle.
Circly. So
Did I say
we
that?
know to parameterize a circle of radius 6, we would go 6 cosine comma 6 sine.
Oh, you chose X as U because that's the easy. Okay.
Yep.
Gotcha. All right.
Mhm. So we could have used the V here and then used there. Doesn't matter. Right, so that's a cylinder. Right, and each cross section of this cylinder is a circle, just like each cross section of this cone is a circle. It's just that here the radius in the cone, right, it's not constant because the radii are changing as you move up the cone, which is why we have a variable in front of sine and cosine. It's just because, right?
Yeah.
Right, those circles are getting bigger, so there's a variable radius. So we somehow have to have a letter that's representing that change in radius.
Why is cosine for y and sine for z? Is that like how it always will be, or is?
Well, you tell me. Would it work if we put sine there and cosine there? We would still get a circle of radius 6. That just changes the orientation.
Okay.
But orientation doesn't matter here. We just want to generate a circle of radius 6. So you're absolutely right. We could have put 6 sine and 6 cosine. All that changes is the way that that circle is graphed in the YZ plane.
So is that the same kind of thing if like it was pulled in the Y direction and we had our U in the middle, then we could put sine or cosine on
Yep.
either?
Yep.
Or,
Mhm.
Okay.
Mhm.
That was,
You know, in our traditional way to do circles is cosine comma sine. That gives us our counterclockwise orientation. But you could definitely swap them. Will?
will MML care about whether we use U or V depending on?
Yes.
That's a good
yeah.
That's a great question.
Yes.
It will.
Yeah.
Yeesh.
I can't remember how it designates what to use for each. I don't remember. I mean, I was just doing a bunch of them and it just seemed natural, but I don't know, we'll see. I feel like it should take multiple, I feel like it should actually be flexible, but maybe it's not. We'll find out, I'm sure. You'll let me know. All right, let's see, was there another one down there? No, okay. All right, so we've parameterized a couple of surfaces. Let's just keep going. Actually, let me do, no, there's one in this set that's I was gonna say let's parameterize a plane also. Should we do a plane real quick?
Yes.
Yeah.
Sure. Just because a plane is so common. There is one that has a plane in it. But in general, notice that if we have a function, so let's suppose we have some surface like z equals, and I said plane, so let's make it a plane. So 5x minus 5y. So that's a plane that's been rearranged and written so z is a function of x and y. Can't you parameterize any function very easily, just like we parameterized in 2 dimensions very easily when we had a curve that was a function? Can't we just go u comma v comma 5u minus 5v? That's a terrible idea to have both these numbers the same. Let's make that different. We want to make sure that we're not thinking there's a pattern when there isn't. How about that parameterization? That makes sense? So we all know, let's recall that when we're doing curves, if we had something like y equals x cubed, the standard parameterization for a curve that's written as a function is t comma f of t. And so the same idea is true if you have a surface that's written as a function. You're going to let x and y be u and v, and then z will be the surface. You're going to use u and v in place of x and y. So just like we do with a curve that's written as a function, we let x be t, and then y is f of t. Here we let x be u, y be v, and z be f of x comma y. Okay, so let's do a couple of real problems. So surface integration. Here is the concept. Concept is very similar to all of the Riemann sum stuff we've been doing forever. So this little region, this little rectangle in the parameter plane, right there, that's going to correspond to a parallelogram. Well, actually, let me say, there's 2 different things it's going to correspond to. It's going to correspond to a patch on the surface, a little tilted patch on the surface, a curved patch. And then that curved patch is going to be approximated by a tiny parallelogram that's in the tangent plane. So we've got our surface, we've got a tangent plane, we've got this little rectangle over in the UV plane, and it lines up with a curved patch on the surface, but then in the tangent plane there is a parallelogram that approximates that patch. So the next slide will show it a little better. But does that make some sense? So every little rectangle in the UV plane corresponds to a little curved patch on the surface. But then we need a way to approximate the area of that curved patch. And so that's what we're going to have to figure out, a way to approximate the curved patch. Just like in other Riemann sum things, we approximated the height, we approximated rectangular areas, we approximated volumes, we approximated all sorts of areas and volumes. So the same idea is going to be true. So let's now zoom in over there. When we zoom in over there, we see the patch is the piece of the blue surface that's exactly below this rectangle, this parallelogram. So that patch corresponds to that little UV rectangle, and we need some method of approximating the area of that patch. And then we have to do the same Riemann sum thing. We have to take the parallelograms and shrink them so that eventually we get exactly the surface of this, the area of this surface. Yeah?
Is this like relatable to going from like almost like arc length parameterization?
Yes.
From going from ds to dr?
Yes. Yeah.
Sweet.
Very similar. Very similar. So we took the ds's and we usually turned them into dt's.
Gotcha.
Right? We parameterized our curve. Same idea.
Light bulb.
Yep. So All right. We have we know partial derivatives already. And what we can do at our point of tangency, we can create a vector, a partial derivative vector in the v direction and a partial derivative vector in the u direction. These may or may not line up with x and y, right? Because the uv plane, the parameter plane, is different than the xy plane. So we don't know that this this t sub u, we don't know that it's pointing in the positive x direction. We don't. Right, it doesn't even matter. So it's relative to u. It's not relative to x and y. But regardless, if we take the partial derivative with respect to u, partial derivative with respect to v, we get two tangent vectors that are coplanar. Those two tangent vectors are going to be emanating from this point, and they're going to be, let's imagine them as tiny little vectors coming from this point, and they're not necessarily the same length, tu and tv, t sub v, and t sub u. And now we're going to scale them. So we have to scale them by delta u and delta v. So delta u and delta v are the height and width of the rectangle in the UV plane. All we're doing is scaling them. And we have to scale them because sometimes we need to have a relationship between the size of this parallelogram and the size of the rectangle that it comes from. So we're scaling it. We can't just use the same, we have to somehow scale it so that as we're letting the little rectangles get smaller, the parallelograms are also going to get smaller. And so the way we scale these two partial derivative vectors is to multiply by delta u and delta v. So t sub v times delta v, that's this red vector. T sub u, delta u is that other red vector. We just have two tangent vectors on the surface. If we cross those tangent vectors, we get a normal vector. If we take the length of that normal vector, we get the area of the parallelogram. Right, the length, so there's tu, tv, we cross them. This is going to be normal to the surface. This is then the area of the parallelogram. And that parallelogram area is approximating the area of the little patch that's right below it. And as you let the parallelograms get smaller and smaller, the approximation gets better and better to the area of the full surface as we add them all up. Okay, so now in practice, we're going back to this thing where if you're integrating a function, you have to somehow have this evaluation piece match. It's got to be the same kind. So here is the first surface integral. We're going to integrate a regular old function. ds, capital DS, means surface differential. That surface differential is a little patch of surface. We're obviously not going to be using that as an evaluation, just like we don't use S normally. We have to convert. So then we parameterize our surface, and that ds gets converted into the magnitude of the normal vector times dA. This is the area of the parallelogram, right there. In a lot of ways, it's like a Jacobian. We take the ds and we rewrite it with this little adjustment factor times dA. So it's acting like a Jacobian would act. It's giving us a little adjustment. The area of the patch is approximately equal to the area of the parallelogram times dA. All right. And remember back with the line integrals, if we integrate a regular function, we take the length. If we integrate a field, we don't take the length. We're going to do the same thing here. So when we integrate a function, we take the length of the normal vector. And when we integrate a field, we won't take the length because we'll want the field to be able to dot with that normal vector. Okay, so also same as other things we've done. If the function in here is just 1, then the integral is representing the area of the surface. Just like a single integral of 1 gives you the length of an interval, a double integral of 1 gives you the area of R, a surface integral of 1 is going to give you the area of the surface.
So that has to be 1 for this to work?
Nope, it has to be 1 if the interpretation of this is area of surface. So if this function is not 1, it depends on what that f represents. So if that f is not 1, let's suppose that f represents temperature. Then you'd be adding up all the temperatures on this surface, and then if you divide it by the area of the surface, you would get the average temperature. So it all depends on what that f means. If that little f equals 1, then the integral means area. If that little f equals something else, then it means something else.
It's not volume.
Volume,
It's usually a double integral of a function's volume, right?
but that's a great question. So the difference is that our domain, we are integrating on the surface. Our function is not defined on the xy plane. It's not building a surface that's above a domain. Now our surface is the domain. Right? So our function is defined on the surface. So instead of the function being defined in a coordinate system, it's defined on the surface itself. Right? So here, that little f right there is associating a number to every point on the surface, and this integral is adding up all the numbers on that surface. This is more analogous to a line integral.
Okay.
So, and I bet we could come up with a volume analog somehow. I just haven't thought about it that way, but I bet we can. I'll think about that. Okay, so surface area using a parametric description. Okay, so we know that the little f is going to be 1 here because we want area of this piece of plane. This piece of plane. So let's parameterize the surface. So r of u comma v. We already parameterized the plane. What do you think we're going to do?
uv 3 minus u minus 3v.
Perfect. Right, so u comma v comma f of uv. So then we find the vector r sub u, we find the vector r sub v, and then we cross the two. So r sub u, we're going to start to notice a pattern. I'm hopeful that somebody will say, oh, couldn't we just have... And I can say, yeah.
Is that just t sub u and t sub v?
Yep.
Same thing.
Yeah, I don't know why they use a t in there all of a sudden. Yeah, because we're just, if you look somewhere else in the book, they say that t sub u is the same as r sub u. I don't know why they switch. I don't know why they call it r t sub u. Most books, if you parameterize using an r, you just call that r sub u and r sub v. Yeah. Now we cross them to find the normal vector. Crisscross.
I'll take the magnitude and that's the area, right?
Bingo.
Yeah.
So normal vector here. So cross out that. We get 0, minus minus 1, so plus 1. This one we get, let's see, we have to use so 0 minus 1, so 1, 3. And then what's the last component?
Just 1.
Last component is 1.
No.
0, isn't it?
Last
never mind.
1 minus 0. 1 minus 0. Now notice that in this case we're dealing with a plane. We could have written our plane as x plus 3y plus z equals 3. And normal vector for a plane is the coefficients. So
Is this the pattern you were talking about?
yes, this is the pattern that I was talking about. That if you're dealing with a plane, this will always equal the coefficients if you put your plane in standard form or general form. Ax plus by plus cz equals d. Okay, but I would not rely on that though. I think whenever you're dealing with a plane, you can get away with doing this. And when you are dealing with a surface in general that's written as a function, there's a couple of shortcuts. I would just get in the habit, r sub u, r sub v, cross them. Just so you have one way to always go at it. And if you start to see the pattern really clearly, yeah, of course, then if you can distill it down to a pattern that works for you, totally fine. But in general, my recommendation, if you're if you're parameterizing a surface and you need to find the normal vector, r sub u, r sub v, cross the two, find the length if it's a regular function, don't find the length if it's a vector field. All right, so now we have to find the length of n, or whatever we want to call it, r sub u cross r sub v if you prefer. That's going to be 1 plus 9 plus 1, so square root of 11.
So that's just the area of the.
So we're almost there. So now we have to plug that into our double integral. So the double integral of 11, and we parameterize with respect to u's and v's, so this should be a du and a dv. And the question then is,
For the bounds.
what are the bounds? So u and v were representing x and y. So if they're representing x and y, what we're imagining then is letting z be 0, and we're projecting down into the xy plane to see what the relationship between u and v is. So we're projecting down into the xy plane or into the uv plane if you prefer. So in the xy plane, which is the same as the uv plane in this case because we let u be x and v be y. So what do we have there? We have x plus 3y equals 3, or we could write that as u plus 3v equals 3. Either way, doesn't matter. This is either u or x. This is either y or v. Doesn't matter. Let's see. So if we let y be 0, then x is 3. If we let x be 0, then y is 1. So there is the domain in the uv or xy plane. Yep.
Going back to the double integral, so I know we talked about if the thing is all 1.
Yep.
How do we know that it's 1?
Because we didn't put anything in there.
Oh, okay.
The thing that we put in there was this. So we filled in that part.
Okay.
That's what the root 11 is. The root 11 is that. So we didn't put, there's no function that we put in front of the length of the normal
So
vector.
then what is, so the plane doesn't go in there at all?
Nope.
Okay.
Yep. It's all by the limits and by that normal vector. So the length of the normal vector goes in there, and then we get everything else just through our limits. So we would use a vertical element, most likely.
I disagree.
Say again?
Disagree. For what you have written.
You want to use a horizontal?
Well, just the way you have it written there is.
Oh, yeah, good point. Yeah, let's use a horizontal. Thank you. We'll use horizontal. So then v is going to go 0 to 1, and u is going to go, let's see, so that's going to be u equals 0 there, and then u equals minus 3v plus 3. Minus 3v plus 3. And there it is. And then we just have a pretty simple integral. Integrate 0 to 1. In here, we have root 11. Actually, let's just pull that to the front since it's a constant. There is no u, so we get the length of the interval, minus 3v plus 3. dv. That is a v, that a u. Make sure. Integrate that with respect to v, plug in the limits, we get the area of that patch of plane. Plugging in 1 gives 3 minus 1.5, so that's 3/2, so we get 3 square root 11 over 2. That will be the area of the plane in octet 1. Math problems that make you say, All right, let's do another one. Cap of a sphere.
Sounds like a book.
Yeah. It's time to start writing.
that make you say?
All right, cap of a sphere. So we want to find the area of that little cap. So same idea. We're going to let the little f in that theorem up there just be 1. And let's project this onto the YZ plane so we can get a better picture of what we're dealing with. So if we project this onto the YZ plane, let's see, we would be dealing with, so in the YZ plane, we're letting x be 0. So that's going to be a circle of radius 2. So a circle of radius 2. And we're chopping it off as z equals 1. So we're going to chop it off at z equals 1 right there. So the thing we're trying to find the area of is that cap right there, but it's rotated around, so it's a little dome cap. Yes?
Why didn't you use XZ plane? Doesn't matter.
Doesn't matter.
Okay.
Yeah. The idea is to use one of the planes so we can just kind of see how the cap is on there, just to get a visual. Because what we're going to have to figure out is phi.
Oh, joy.
Find phi. Where's phi? So, yeah, we'll get to that. All right. We will get to this. Parametrizing a sphere. Parametrizing a sphere. So when we are parametrizing a sphere, we are going to have flashbacks to a coordinate system. Spherical coordinate system. So let's go back to basics. Back to basics here. Remember that first we started with cylindrical. Cylindrical was r cosine theta, y was r sine theta, and z was z in cylindrical. Z was z. Then we had that fancy triangle that related r, z, and phi. And that's how we replaced these things. So then we went to spherical, and we said, oh, r is equal to rho sine phi. Rho sine phi. So that went in here. Rho sine phi. And here we went rho cos phi for z. All right, so that was from that triangle that relates r, z, and phi. So those are spherical. All right. Now, our sphere has a constant value for rho. What is rho?
1.
No.
Pi over 4.
No. 2.
Pi over 4.
2. Right? Because that's x squared plus y squared plus z squared equals 2 squared. It's a sphere of radius 2. Rho is representing the radius. So for us, here's our clever way to get to our parameterization. So our parameterization, r of u comma v, is going to be 3. And we can either let u be phi or u be theta. Does not matter. Let's just go in order here. Let's just make this 3 sine u cosine v. I'm going to move this so that I have more space.
What? Where'd you get the 3 from?
No idea.
The 3 came from, good question. Yeah, what should that be?
2?
2.
Okay.
Yes. It is the 2 that you, yes.
Please explain.
Yeah, where'd that 3 come from? Okay, so
You even
that.
said 3 too. Sometimes you do like one or the other. You write something
Yeah.
wrong and then you say
Say
it
it
right or
right,
something.
Or
You did both.
say it wrong and write it wrong.
You are human.
Human. That's how you have to program things, so you think they're human when they're not.
Oh.
It does what you want, what you
That's
tell
what
it to do,
Yeah,
not what you want it to do.
exactly. All right, so that's our parameterization. If we let all the phi's be u, that's our parameterization. So that's a sphere of radius 3. That's a parameterized sphere of radius 3. That's a parameterized sphere of radius 2. I promise. That's a parameterized sphere of radius 2.
So that's letting.
Why did we cross out the x at the top there?
I crossed out the x just because I was projecting into the YZ plane so I
Okay.
could get a visual of how far this cap went. So we need to now tell the program what u can be and what v can be.
So u is phi and
U is phi.
is theta, right?
Yep. So v is easy. That's going to be 0 to 2 pi. Right?
Yes.
Okay, u is hard because that's phi, and phi is always hard. We have to figure out, okay, we start up here at the positive z, and then we're rotating. We have to figure out where that intersection is. So we have to figure out that intersection. So if we look at this circle right here, we're trying to find this angle in here. That's going to be our phi.
And then are we going from there
not too
to,
bad.
can we go from there to pi over 2 and double it? Or go from there to pi?
And that's going to be equal to u.
Oh, how would the fact that we're doing the cap and not the whole
Right now it's
sphere
pi over four.
come
Well,
into
we're
play?
not even there yet. We'll get there. We'll get there. We'll get there. Let's first figure out what the, so this, if we let u go from 0 to pi, and v goes 0 to 2 pi, that's the whole sphere. So we're going to get to just the cap by allowing u to only go from 0 to,
Pi over 4.
let's see. So if we look in the yz plane, this z value is, what's that z value?
1.
1, all right? The z value is 1. So in yz plane, or you could have done xz plane, doesn't matter. This is just to get our relationship. So we're going to let z be 1 right there. So we're going to have y squared plus 1 equals 4. So y squared equals 3. Positive square root of 3 will be that height right there. So this point right there, we just calculated that y is square root of 3 and z is 1. Whoa. So what is phi then?
It's going to be pi over 6.
Phi goes from this direction though.
Pi over 3.
Pi over 3.
Pi over 3? Everyone agree?
Pi goes from this axis.
Pi over 3.
We'd also just z equals rho times cosine phi, and then could have solved phi, right?
Yes.
That might be an easier way
Yep.
to do it.
I mean, that's basically you have to get at the same type of thing. You're going to have to do an inverse cosine. Yeah.
Okay, is that doubled?
No.
Why not?
Because we're only finding the upper cap.
Yeah, but you only have from the z-axis to that.
But then theta goes 0 to 2 pi.
Oh, so it gets
that's
the
going
other
to pull it all
half.
the way around.
Okay.
Yeah. It's going to pull. It's going to get the whole cap.
How did you get y equals square root of 3? Did you just plug in like a z value?
So in the yz plane, x is 0. So this is the projection into the yz plane. And then this line right here is z equals 1. So we're going to plug 1 in there to figure out what this is. So that tells us then that the slope of this line, that's a bad color, the slope of that terminal ray is 1 over root 3, or it's root 3 over 3. And we know that on the 12-sector circle, that picture's not great. Oh, this pen is dying, yikes.
No.
That puts us right here where this is 30 degrees and this is 60 degrees.
There's a blue marker on your desk.
Oh,
Wow.
instead, I don't want to use the end of your pink.
It was fine.
I looked away for 1 second and I feel like I'm being elaborately pranked because the thing that was just pi over 3 is now 1.
It's now 1.
The-
How did that happen?
Wait a second. He's
What?
right.
Did I hit undo or something?
I'm so confused.
Yeah.
Yeah,
She's
that's,
being pranked.
you are being pranked. I don't
Thank
know how
you.
that happened.
Pointing at
I
that.
must have hit the undo. I'm glad you pointed that out.
We're all just like okay with it, you know?
Yeah.
I would like to go back in
must
the
have
lecture and like,
hit that somehow.
what happened.
Oh, interesting. Okay, so everybody clear on how we're getting to that? The slope on the 12-sector circle right there is root 3 over 3. The slope right there is root 3. But we're coming from this direction, so we're going 0 to pi over 3. So those will be our u limits. So if this went 0 to pi over 2, we'd be getting the upper hemisphere. If it went 0 to pi over 6, we'd be getting the tiny little cap. This went over to pi over 6, getting the Arctic Circle. Yep.
So you said that just because phi starts at the z-axis, and that's because that slope is definitely root 3 over 3, which corresponds to pi over 6, right? But
Yeah,
you're saying
so
that-
this side is pi over 6.
Right.
But
Okay.
phi goes from this.
So phi is coming from up there, though. So when the slope is root 3 over 3, we've gone pi over 3.
Okay.
All right, let's take our break and then we'll find our normal vector because that's going to take
We're
some.
not even done. What is even the point?
We were trying to
What are
find
we
the.
doing?
We were trying to find the area of that spherical cap.
Oh, yeah.
We're finding the area of the spherical cap.
I totally forgot.
The
Right.
surface area of it?
Yes. Surface area of it. Surface area of the spherical cap. That's what we're doing.
And then,
Okay, so there's our cap.
Are we doing?
Now we need the normal vector for our cap. So we find r sub u, we find r sub b, and we cross them. That'll be the normal vector for the cap. So r sub, who did that?
Do any of us know how to do that?
Yeah, you could just lean against it probably, and something weird would happen. All right, so r sub u, we do. Oh, Haley, I thought about your question. If that function represents, so we have if we're on a surface, and the f function is representing the height above the surface, you can think of it as finding the volume between the surface and the that function.
Okay.
You can. It's not the easiest to conceptualize, but you could think of it as volume. If that function is representing height, then you're finding volume. Okay, so partial with respect to u. Partial with respect to v. Be very careful with your u's and your v's.
Why do they have to use U and V?
I know.
Come on.
Right.
Come on.
It's like they use the worst possible choice.
Worst possible letters.
Well, you know, we could have it worse. We could live in the Middle Ages and have all the U's written with V's instead.
Oh, wait.
Okay, so then we find our normal vector by crossing these.
Oh my goodness.
bless you.
I think bless you. All right, so that's 0, and then that multiplied by that is going to be 4 sine squared u cosine of v. The middle one is going to be 4 sine squared of u sine of v. And the last one is going to be sine u, cosine u, cosine. So 4, that's not easy.
Oh, so it's plus and minus.
Very coordinated.
How does the last one work?
Oh, I see it. It's happening. 2 cosine. Wow.
V squared.
Okay.
Okay.
So the last one is this times this, so we get sine u, cosine u, but then cosine squared of v, and then plus 4 sine u, cosine u, sine squared of v. So that one's going to simplify a lot in a second. All right, so now we
It's
have.
just going to be 4 u, sine u, cosine u.
Say that again. On the end,
Yes.
this one is going to be 4u cosine u, yes.
Or sine.
For sine u, cosine u, yes.
Okay.
Yes, for sine u, cosine u. I'm speaking a different language. For sine u, cosine u. Sine u, cosine u. All right, so then we find the length of this thing.
Oh, wow.
Yeah.
That last portion of it is a nightmare.
This whole thing reduces to 4 sine u, cosine u.
Very nice.
Is that just because of the addition?
Because the 4 sine u, cosine u is
Cosine
common to
squared
both,
and
and then we get cosine squared plus sine squared.
Oh.
Snap. Gone. All right. And there was no simplification in the first one, though, right?
Both
That's
of those.
right. That's just that's not going to simplify yet. All right. So then we
Thank
square
goodness for that
these.
0. Thank goodness for that 0.
Let's square this one. So we're going to get 16 sine to the 4th of u cosine squared of v plus 16. There's going to be some simplification in just a minute. Sine squared of v plus 16 sine squared u cosine squared u,
There we go.
all to the 1/2. All right, these first two have some cancellation, right?
Yeah.
This first pair all turns into 16 sine to the 4th of u. Everybody agree with that?
Yes.
Because we have a sine squared plus cosine squared of v. And then that, we can factor out 16 sine squared, and we're going to get, we're going to get 16
Are we
factored.
gonna get 16?
Say again?
So you factor out, this is still on the square root, right?
Yep.
So if you factor out that, then you get sine squared plus
Cosine squared, which is simplifies tremendously.
Wow.
And then it's going to simplify more when we factor out 16 sine squared of u. We're left with sine squared of u plus cosine squared of u.
Yeah.
All to the half. So then
it's just a square root.
Sine squared.
4 sine of u.
Yeah. That's awesome.
4 sine u. 4 sine u.
Do we know it's positive?
Yes.
How?
How?
Yes.
Because
Oh, is this still a sphere? Okay.
because if we look at the values for u, the values for u are creating positive signs
And we're definitely in a positive.
on that cap. Yeah. And u is representing numbers that will give sine of u being positive. Jalen?
Why would you know to use spherical for this instead of?
Because it's a sphere.
Okay. That's it?
Yeah, that's it.
Okay.
Yeah, spherical. Yeah, so we'll use combinations of spherical and cylindrical, depending on what we're dealing with. Bless you. Because it's a sphere, though, that's why. Okay, so let's go back to our integral. So we were just finding the area of this cap. So there's no function in here. All we're dealing with is that as the length of our normal vector. And we're dealing with those two intervals, 0 to pi over 3 and 0 to 2 pi.
I'm gonna have room on my paper.
Well, we're gonna do a vertical,
There's no way he's gonna
right?
give us this one.
So we are doing, what do you mean vertical? We have a rectangle. Because
With the cap thingamajig, we're doing a vertical element on the cap.
we're not even dealing with elements anymore.
We found that out.
Because
Right.
we switched our domain to be in the UV plane, and U goes from 0 to pi over 3, and V goes 0 to 2 pi, so we're just on a rectangle.
Well, does it matter which way we have?
It matters because we have the U in here, so we have to have the du on the inside so that we can integrate with respect to U.
Okay.
Because if we, actually,
It should.
no, it doesn't matter. You're right. It doesn't matter. You're right. It doesn't matter because it's a rectangle. When it's a rectangle, it doesn't matter. Does not matter. Good point. So there's no v in there, so we can do 2 pi times 4 minus cosine of u, 0 to pi over 3. So that's going to be 8 pi times cosine of pi over 3, which is 1/2, minus cosine of minus a minus, so plus cosine of 0, which is 1. So we end up with 4 pi.
Yes.
Did you get that?
Yes. I did.
Excellent. Well done.
Thank you.
Well done. All right, let's go to the next problem. That took too long.
Look at look.
That's a lot of work.
Yeah.
Wouldn't it be a negative 4 pi?
It's if you leave the minus in here, it's cosine of pi over 3 times minus 1. What did I do here?
And we
Hold
still
on.
have to do flux.
8 pi. Cosine of pi over 3 is 1/2.
Yeah.
Oh, no, it should be, it's going to be positive 1/2, but the way I wrote it's a little goofy. It should be more like that.
One thing I'm confused about is how we got just the cap and not just the cone.
We got the cap because we parameterized the sphere and only allowed u to go 0 to pi over 3. So we're not using spherical coordinate. We didn't integrate, we didn't do a rho squared sine phi thing, rho squared sine phi. We didn't do.
Well,
All right.
So imagine this is your top half.
All right, so let's do another one here. So now let's deal with this cylinder. So surface integral, now we have a function that's not just 1. So we're going to find something other than the area of the surface that we're dealing with.
So this could be like temperature, like you were saying.
Yep, so this could be temperature, could be density, could be height.
What I thought is.
All right, so let's parameterize our cylinder.
We were just, all we wanted was going up, yeah.
Yeah, so that's
So-
exactly what happened. So since you went.
So this cylinder is a vertical cylinder.
This area
Oh.
that's gonna have a-
So Z is the easy variable. Z goes 0 to 3. So let's do this kind of
That
thing.
makes a lot more sense.
We'll let that be V. That's going to go 0 to 3.
And then that's a circle radius.
And that's a circle of radius 3.
Just 3.
So this is going to be 3 cosine U, 3 sine U.
Hey, it's getting.
Does that make sense? So it's a vertical, right circular cylinder opening up. Radius of that is 3. So now this 3 in front is from here, right? It's not from there. So the 3 in front of the cosine and sine is from the square root of 9. And now we have to put our limits or the range for these two variables. So U is going to go 0 to 2 pi. And V is going to go from 0 to 3. Let's find our R sub U and our R sub V. So we take our derivative with respect to U. Take our derivative with respect to V.
I knew once I'd heard short ones, I knew it
You
was
knew
0,
it was
0, 1.
zero
I was
before you
trying to
even
do
looked?
something really complicated, and I was like, oh wait, no.
Yeah, it's going to be fast. It's going to be fast. So our normal vector is pretty nice. We already know the y component's got to be 0, right? It's a right circular cylinder. Normal vector pointing out. So this should just confirm, oh, we get 0. And then the z component. Oh yeah, of course. Also 0, right? We have a right circular cylinder. The normal vector is horizontal. So is it the y coordinate? The z coordinate's definitely 0. I think maybe the y coordinate I have wrong.
Yeah.
Yeah, the z coordinate. Why was I thinking the y coordinate? The y coordinate is 3 sine of u. Oops. Yeah. Right. So the
x coordinate negative.
positive.
Oh.
Main diagonal minus that diagonal, and then that, and then that. So if we think about the right circular cylinder, the y's and the x's are both changing, but the z's are all 0, right, for the normal of a right circular cylinder. Right, z is 0. Okay, length of this vector is 3. Yep, square root of 9.
Oh.
And then we have our double integral. The function they said to integrate was y. So we go to our parameterization for our surface and pluck off y. So the parameterization for our surface is right here. So that's what y is equal to. So 3 sine of u. And then du dv. We had just a rectangle, so it didn't really matter. 0 to 2 pi and 0 to 3.
How did we get that bound 0 to 3? I think I might have missed that. Is that from the equation up top?
So the 0 to 3 for v is because we let z be v, and z was, we were told, was 0 to 3.
Okay.
So that part. And then there is no v, nor will there be a v, so we can multiply by 3 from the outside. We integrate sine and get minus cosine. And we go 0 to 2 pi. And so that's minus 27 times cosine of 2 pi minus,
It is 0.
yeah, 0. Very unsatisfying. Let's think about why it might be 0. So the function that we're adding up across this surface is y. So we look up at our surface, our cylinder We're adding up all the y values between 0, z equals 0, and z equals 3. There's just as many negative y values as positive y values. Right? Just as many. Even number. They all cross out. Yep, gone. 0. Parabola here. Paraboloid. Paraboloid.
Will we always be told this f, x, y, z kind of thing is what it is, or is that just kind of?
Yeah, we say that once again.
Will we always be told that the function is that, not like, oh, find the function?
Yeah, well, the function will always be provided.
You can't go backwards. There's no backtrack.
No, we'll be given the function.
Okay.
Yeah, the function is, yeah, it's definitely going to be given. And the function really doesn't matter so much. It's the surface that's the hard part, because once you parameterize the surface, you turn your function into a function of whatever u's and v's. All right, so we've got a paraboloid. What letter is the easy letter?
Z.
Z. Z is the easy letter. So we have R of u comma v. And which letter, what do we want to plug in for the Z? V. Okay, great.
Okay, great.
Okay, great. That's just great. All right, so there is our setup. What's each cross section? Horizontal cross section for a paraboloid opening up. Each one's a circle. The radius is changing though. So we can't just put cosine of u, sine of u. The radius is changing, so the front has to have some sort of function to indicate that the radius is changing. So we go back up here, and we convert to polar, and we see that z is equal to r squared. So r is equal to the square root of z. We said that z was going to be played by v, so this should be
Square root of z.
square root of v.
All right, now let's do this on the test next time. It will be perfect.
Exactly.
Z and he gave me the funniest.
Well, it's the same thing.
I know. Z is v. And then what does u go from? 0 to
It's kind of like
0 to 2 pi because it's representing the radius, or the, the angle. Okay, now we find r sub u, r sub v, and cross them. R sub u, r sub u, r sub v, r sub v, so we have half v to the minus 1/2. Okay, I think that's pretty good. Oh, why did I put a minus
why'd you
there?
put-
Yeah, I looked up here and saw that minus. That's,
Yeah, I think.
Wouldn't that still be cosine?
yeah, I looked at the wrong one. Sorry, I looked at the derivative with respect to u instead of the original. That should be cosine of u, and that should be sine of u.
Shouldn't it be negative?
it should be negative, right?
Yeah.
In the which one?
Both.
Both of them, because
So when we partial with respect to v, we're going to get
Because you. Oh wait.
partially with respect to v, we get 1/2 v to the minus 1/2. So the partial with respect to v both should be positive. But these should be the originals, not from
We're thinking
there.
of something.
else. Yeah.
And now we cross products.
Now cross them. Crossing them will give us our normal vector.
Does that say cosine UU?
That says cosine uu. Yeah, cosine uu. All we need is one u. One u is enough. One u only.
One U is
So the first component is going to be square root of v cos u.
Oh, I can see how this is gonna.
The second component is going to be square root of v sine of u. The third component,
1.
it's going to be 1?
I think so. Yeah, just the
I'll trust you.
negative sine u and
Not negative one?
It's negative.
Negative one, sorry, misread
Negative
it.
one, okay.
Misread what I wrote.
Yeah.
Hold on, but hold on. Because those are over 2.
Okay, let's
so
see.
wouldn't it be
Yeah,
negative
so
1/2?
yeah, let's see if you're. So that's going to be a sine squared. That's going to be a minus 1/2 when we multiply those
Yeah,
two.
so it'd be negative 1.
So minus 1/2 sine squared plus minus 1/2 cosine squared. So it should be minus 1/2.
All right, I didn't see those twos.
Yeah, those twos matter.
Those two.
Okay, those twos matter. And now we're integrating a regular function or a field.
This is a function.
Function, so we have to find the length of that. If we were integrating a field, we could just dot it with the field and we'd be running. So the magnitude, so we square everything and then take the square root.
So that's going to do good.
Yeah, there's often a whole bunch of nice simplification of these. So we end up with the square root of v plus 1/4. Okay. Now we go back to the original integral. That's our Jacobian type thing. And this, I think, did have a function. X squared plus y squared. We have to go to our parameterization. There's x, there's y. So when we square this, we're going to get v cosine squared plus v sine squared. So that's just v. So x squared plus y squared is v. So we're going to have v multiplied by the square root of v plus 1/4. And then dv, du. Doesn't really matter the order since we're dealing with a rectangle. V is 0 to 4.
Oh, don't use
That would be so
we have to do
confusing.
U sub. Oh, crap.
Well, let's do x sub.
Yeah, we have to do a substitution. All right, well, you guys can do this one on your own. You can choose your own fancy letter. So you'll let whatever letter you want equal v plus 1/4. Call it x. dv will equal dx, and then you have to subtract the 4th, and you can integrate that easily.
Why do we use so many letters so that we can't use other letters now?
That's why we're using Greek now.
I know. We need like multiple.
We're
We need to
out.
extend our alphabet.
We don't, because
Let's petition the government.
English is hard enough as it is.
I don't know, I heard of one language that had 84.
All right, so next.
Yeah.
Now let's do an example where we integrate a vector field.
Chinese.
So those other ones, we integrated a regular function.
Yeah.
So we had to find the length of the normal vector. Notice that here, we don't find the length of the normal vector. We just dot it right in, just like with our line integrals right there. Same idea. If it's a vector field, just dot it right in. Don't worry. Don't stress out about this one yet. We will get to it and why it looks so different. We don't need to make it that different looking. Don't stress about it yet. Stress about it later. Okay, so just as proof that this technique of evaluation works, the idea first is that we replace the ds with the length of the normal times dA. We replace the normal vector with a unit normal. These things cross, and this is just verifying that we can do what we have normally been doing in terms of evaluating.
So it is 100% okay for us to write on a test convenient cancellation?
Convenient cancellation.
Just write it out there?
So convenient.
Just jump steps, just like convenient cancellation.
And by convenient cancellation, we get 0.
Plus it's 0.
Okay, so surface integral of a vector field on the face of a tetrahedron.
Last page.
So we-
page.
Is this the last page?
Yes.
Good, because we're going to get to the next notes. All right, so we have this nice tetrahedron. We have this tetrahedron, this face that we're going to look at is in quadrant 1. We have z-intercept of 10. The x-intercept is 5. What's the y-intercept? 2. Y-intercept is 2. All right, so we've got the face of this tetrahedron right there. Okay, so that's our surface, that tilted triangle. That's our surface. Let's go ahead and parameterize our surface. So parameterizing the surface is going to be pretty easy because it's just a plane. So we do u, v, and then plug in the u and the v for x and y, and we're golden. So there's our parameterization. And now you're going to start to see how this unravels very quickly. So when you cross them, we all know what we're going to get, I think.
Oh, well, we should have done that.
251?
I forgot.
Oh, yeah.
So with a plane in the first octant, like this, or it doesn't even have to be in the first octant, this RU cross RV is always going to turn out to be the coefficients if you put it in general form. If you wrote it as 2x plus 5y plus z equals 10, 251. Okay,
We
so
don't
it's
have
always,
to find the length.
what's that?
We don't have to find
We don't have to find the length. So we have to take our vector field and convert it into a vector field based on our parameterization. So our vector field is going to be x, y, z. So that's our vector field right there. I think we can dot it in one step, right? So we're going to take these two, that. Since those are, the vector field is just a radial field. And we're going to dot it with that. So we dot those two together. We're going to get 2u plus 5v, how convenient, plus 10 minus 2u minus 5v. du dv. Oh.
We didn't do our limits.
Yeah, we didn't do our limits yet. We'll get to those. We'll get to those shortly. This all simplifies to double integral of 10 du dv. All right, let's figure out our limits. So because of the way we parameterize u and v are the same as x and y, we have to just go down and look in the xy plane. So in the xy plane, let's do this. That's going to be y equals minus 2/5 x plus 2 in the yx plane, xy plane. And if we're letting u represent x and v represent y, did I do the right order there, or should I swap them? If we want to use a vertical element.
Switch them.
Switch them. Let's switch them.
Does it matter though?
You just have to solve the other way around. Doesn't matter. But it's not a rectangle, so it does matter in the big picture. We have
So the grand scheme of things, it does.
In the grand scheme of things, it does. So we'll go dv to u. U comes from the constant interval 0 to 5. V comes from the interval 0 to minus 2/5 u plus 2.
By limit.
Indeed. So then we factor out the 10. We have the interval 0 to 5. There's no v, so we get minus 2/5 u plus 2 du. And I've run out of space. Simple integral. To use the power rule, plug in your 5, plug in the 0. Good to go. Let's get to the next hard one. Setup on these is so critical. Okay, next one. So we've got our vector field again. We have a cylinder, not a right circular cylinder, but a parabolic cylinder, a trough thing. And then x is coming from 0 to 1, z is coming 0 to 4. And they give us an orientation. They say the normal vectors are pointing in the general direction of the positive y-axis. So let's see if we can get a sketch at least so that we kind of know what's happening. So y is equal to x squared. So that's going to be a parabola opening this way. And we're only in the first octant because x is going 0 to 1. It doesn't go back into the board. And z is going to go 0 to 4. So we've got something that looks kind of like that. So there's our cylindrical surface. All right.
Do we have to draw pictures?
We don't have to.
It's just,
It's helpful when we're looking at orientation. It's helpful. Okay. So let's go ahead, parameterize our surface, find our normal vector, and then we'll take into consideration what they mean by this thing up here, where the normal vectors point. That we will manage in a minute. So our surface parameterization, R of u comma v, pretty simple here. Because we have a function, so we can let x be u, and then y is going to be u squared, and then z is going to be v. And we just have these limits, u 0 to 1, and v 0 to 4. So we have a rectangle. So we find our r sub u. We find our r sub v. And then we cross to get our normal vector. And here's where we have to confirm that the normal that we get is doing what they want us to do. And if it doesn't, we multiply by -1. So cross these, we get 2u. We get -1. We get 0. That's what we would expect. It's a cylinder. Should have a z equals 0. So now, is this the correct normal vector, or do we need to scale by a factor of -1? So the normal vectors in general, or the normal vectors point in the general direction of the positive y-axis. So let's see. Do these point in the direction of the positive y-axis?
That looks pretty negative. I don't know.
So let's pick an exact point so that we can really visualize what's happening there.
1, 1, 1.
So if we pick a point on our surface, you want to pick, what'd you say, 1, 1, 1?
Yeah.
Okay, so let's pick 1, 1, 1. It's about right there. So that point right there is 1, 1, 1. And if we want the normal vector at that point, so n of 1, 1, 1. Okay, this point right here, that's in the xy plane, right? So now we have to translate it over. So what is u for that? Well, it's going to correspond to just 1, 1, 1 in the uv plane. The u with u's and v's also, right? Everyone agree that that's going to be just a 1 for the u? X and u are equal, so that's going to be a 1. So 2, -1, 0. So 2 is in the x direction, -1 is in the y direction, and then 0. So that normal vector is pointing something like that. Not in the positive y direction. Right? It's pointing more in the negative y direction. So we convert this. All we do is multiply by -1. And we're good. The y value is positive now. So now it's pointing in the relative y direction. Positive y direction. All right, so our field is -y x1. So we go to our parameterization to convert our field into u's and v's. So we convert our field, so we're going to have double integral, field minus u squared, comma, u, comma 1, dotted with the normal that's now pointing in the direction that they suggested. And then du dv. And we said that u is coming from 0, 1, and v is coming from 0, 4. So we get that. Dot these two together.
Wait,
and
how are we going from 1 to 1?
That's a 0. 2u cubed plus u. du. And now we're down to something simple. Down to basics. Down to Calc 1.
Should you get rid of your first integral?
We can get rid of the first integral, absolutely. Yeah. You guys can do the rest of that
I
one.
think the answer's 4.
Answer's 4? Do you agree?
You're so excited.
That's like such a nice answer.
Well, because then you get, when you do.
Because we get 4,
4
we
divided
integrate
by
the.
2 is 1/2, and then you get 1/2 in front of that.
So we get 1/2
1
plus
1/2.
1/2. Yeah, yeah. That's it. I agree. Yeah.
Where does that first vector come from? in
This
the integral?
one?
Yeah.
So this is the vector field
Uh-huh.
turned into u's and v's.
Okay.
So it's the vector field evaluated at the parameterization.
Oh, and then negative y is just negative x squared.
Yes.
versus u squared. Okay, got it.
Right?
Why are there 2 integral curlies but only one du and no dv on the
Why
bottom
said
there?
you should get rid of it? Because there's no dv.
Aha.
Yeah. Yeah, we'll multiply the dv. Yeah, thank you. Yes.
So when we have something where, like it says here, normal vectors point in the general direction of the positive axis, like an axis,
Mhm.
is that the process we take is to find a point on the
Yeah,
field?
on the surface.
On the surface?
Yeah, on the surface, and then find the normal at that and just see if it's pointing in the same
By
relative.
plugging it into r sub u? Is that what you did?
We plugged it into, so this point right here, that's the normal.
Yeah.
So we just have to figure out, if this
Oh.
is x, y, z, we have to figure out what the u value is, or whatever the u's and the v's that correspond to that x, y, z.
So you just plug, only the one goes in there, because there's only, okay.
Yeah, because the
Okay.
u is the only letter that was in there.
Okay.
Yes. Oh, cool, done. Next page. All right, next, 14.7. All right, that was the hard section. Now we get an easy section.
This one's
Not like 14.5 though.
4 sides.
Not that easy. Green's theorem, circulation. Gx minus Fy, we've talked about this a bunch. That's really just curl. It's the normal component of curl. It's the z component of curl, if you're in two-dimensional space. All right, we had, if you did the whole curl matrix, you get 0, 0, that. So that's the, in 2 dimensions, we would call that the normal component, the k component. Okay, so here we're extending to surfaces, and it's super simple. This was in the xy plane. Now we just bend our region in the xy plane, and we have a boundary. Right? So this C is the boundary of R. This C is the boundary of S. There are an infinite number of surfaces that are going to have that same boundary curve. You could imagine a dome. You could imagine a paraboloid. You could imagine an ellipsoid. You can imagine a cone. You can imagine a million surfaces that have this exact same boundary curve. And this theorem is saying that you can do the line integral of the boundary, along the boundary, or the double integral of the curl all throughout the inside. So whether it's a paraboloid, whether it's a dome, a hemisphere, whether it's a cone, all of those surfaces are going to have the same exact value for this circulation integral. The surface will not matter. Wow. The surface will not matter. Okay, so back in two-dimensional space, when we did the matrix form of the curl, we got 0, 0, gx minus f sub y. And that's what this is. Now that we're in 3 dimensions, the curl is not going to have 0, 0 as the first 2 components. We still want the normal component of the curl for the same reason we talked about last time. The normal component of the curl is the part of the curl vector field that gives you the spin. If you spin off angle atop, it's only the normal component of that spin that's going to give you rotation. So that's what this is doing right here. This is taking the normal component of the curl and integrating it over the surface. So normal component of the curl throughout the whole surface generates rotation along the boundary. So we can either integrate the circulation integral around the boundary, or we could add up all the normal components of the curl throughout the whole surface. Either one of those will give us the same answer. Let's try it. So S is the upper half of a sphere of radius 2. Not 3. 2. Radius 2. Not 3. Not any other number. I'll make that 2 nice and big. Radius is 2. I will not forget. Okay, so there's our sphere, circle, and they say verify Stokes Theorem. So verify that the line integral and the surface integral of Stokes Theorem are equal for the following vector fields, surfaces, and closed curves. Okay, counterclockwise orientation, blah, blah, blah. Okay, so to use Stokes Theorem, we are going to do one or the other. So the line integral around the circle, or the double integral of the normal component of the curl throughout the whole region. So let's first do the line integral part. So the line integral part, what is the equation of that circle down in the xy plane?
X squared plus y squared.
So there's our circle right there. So if we want to parameterize that curve and do a direct line integral, do a circulation integral, the parameterization of this curve is r of t is equal to 2 cos t, 2 sin t. And t goes 0 to 2 pi. The derivative of this looks like that. The vector field right there, our vector field, we need to take our vector field and take the parameterization for that curve and throw it into the vector field so that we get the vector field in terms of t. So we're going to have 0 minus 2 cosine t, comma 2 sine t. So there's our vector field. So now the integral around this closed curve, we're going to go 0 to 2 pi. We're going to do f dot r prime. R prime only has 2 components. So we'll just add a 0 for the z component. We can imagine it in 3-dimensional space with a 0 as the z component. So we dot these 2 together, and we get negative 4 cosine squared of t dt. So we dot those 2 together. And we imagine a 0 as the 3rd component. Yeah?
Why are we keeping the circle on the integral? Have we ever done that before?
I really shouldn't put it there.
Okay.
Yeah, we don't need it there.
Sorry.
Yeah, no, good point. Because we've turned it into a regular integral, not a line integral anymore. As soon as we have limits of integration, we've converted it from a line integral to a regular integral. So yeah, we do not need that circle. Thank you. Do not need that circle. Yeah. Yeah, as soon as we parameterize the curve and plug it into the integral, we don't need that little circle anymore. Okay, so that's an easy integral. We end up with negative 2 integral 1 plus cosine of 2t dt, 0 to 2 pi. And that is going to be negative 2, and we're going to get t plus 1/2 sine of 2t, 0 to 2 pi. So we get minus 4 pi.
Why is that?
What does your question mean?
Like, why is it negative?
In terms of the vector, okay, conceptually?
Yeah.
So we're looking at tangential components going around this boundary. So we're going counterclockwise around this boundary. So it means that the tangential components are going the opposite direction. So if we were to look at all the tangential components that are around that around the edge, there's going to be more pointing behind us than in front of us. Right? Because we're going counterclockwise around it. It just means that there's more pointing clockwise than pointing counterclockwise. Right? Because this is FDR. Right? This is the regular tangential, adding up the tangential components of the field. And so it just means that there's more tangential components that are pointing in the clockwise direction than the counterclockwise direction.
Can you do like a simple drawing of that? So people can see? Is it possible?
Yes. So if we look at this circle here, our orientation is counterclockwise. So this just means that the tangential components have, so if we do vectors that are like this, then that tangential component is pointing counterclockwise instead of clockwise.
Sure.
So
Does that make that doesn't affect the curl though?
we haven't done any curl yet.
Oh.
The curl is what generates this movement around the boundary.
Okay.
So when we find the curl will generate this, it should generate the same rotate, it should generate the same volume per unit of time.
Okay.
So, but this vector here has a tangential component that's in the clockwise direction. So it just means there's more clockwise than counterclockwise. Grant?
I have a question about the definition of Stokes Theorem.
Yes.
It says, let S be an oriented surface in R3 with a piecewise smooth closed boundary C whose orientation is consistent with that of S. How does it want the boundary of C to be consistent with S? Is that like the right-hand rule?
Yes.
Okay.
Exactly. That's
Okay.
exactly it. So if we're going to go counterclockwise around this, then the normals are pointing out. So when we look at Stokes' theorem, one side is a surface integral. Right here, let's see. So this is the surface integral, and it has a normal vector. So that normal vector has to line up with this curve. So the curve side, we always go counterclockwise for the oriented curve. And so we just have to make sure that that normal vector and the oriented counterclockwise part for the curve match. If they don't match, then there'll be a -1 in front. Right, if we integrate the curve counterclockwise and get a value, but the normal for the surface is pointing in instead of pointing out, when we do the double integral, we would end up with -1 times instead of exactly equal. So it will always be exactly equal as long as the normal is lined up properly. And properly means the right-hand rule. Yeah, okay, let's do this. Oh, we didn't do the second part yet. Okay, so second part, let's put a little space there. So the second part, we have to find the curl of the vector field and then add up the normal component of the curl. So let's find the curl of that field, 0, -x, y. So curl, we use this crazy looking matrix to find the curl. And the curl is going to be a vector field, what's that, -1, comma, middle component, that's 0. The z component is going to be, I think I messed up the first component.
Yeah, isn't it
Don't
just
you
one?
cross out the first
Yeah, I
row?
crossed out the wrong row. The
Okay,
first component,
one?
the first component is 1 though, right?
Yeah,
Yeah.
first
One.
one is 1, just not negative.
Not negative. The last component's going to be -1. The k component will be -1 minus 0.
There we go.
Okay, so that's the curl. That is the curl. Now we have to parameterize our surface, which is a sphere, which we've already parameterized earlier today. So we've got to use the whole, spherical coordinate thing. There is no way this problem is going to fit on the same page as this problem.
You don't say.
Yeah.
You didn't give us enough space again.
I know. So I was waiting for that.
The big brain solution is not to print out any of the notes.
I know.
That's what's
Absolutely not going to be able to keep
Or
up.
You just have to have some blank paper.
Or you just use the back page.
Back page. Exactly.
You must hate the environment or something.
I'm trying to
These paper are crazy on both sides.
Okay, so now parameterization of this sphere. What's the radius of this sphere?
2.
2. So the parameterization of our sphere,
Oh, no, we're doing this.
here we go.
Okay.
And
2, that's the rho. Sine phi, and what are we going to let be phi?
I know, they always
I don't
have
either.
the damn sun.
Just copy paste from the other problem.
B?
Yeah, absolutely.
Oh.
Okay, there's our sphere parameterized ever so nicely.
You didn't write 3.
What's that?
You didn't write 3.
No, that's the radius is 2. Radius is 2.
Almost have though. Almost have.
Okay, so then we have to do our r sub u, r sub v thing. With the other sphere that we did, the radius was
2.
2. Tell me what the normal vector was.
Was that in the last chapter?
Yeah, it was in the last chapter. Instead of going to do r sub u, r sub v, crossing them, we had a lot of cancels.
Sine of u, I think.
What was it?
4 sine of
Or sine of u.
That was the magnitude of
Oh,
it.
sorry.
N?
It was 4.
Oh, but we don't need the magnitude?
Yeah, we don't need magnitude yet. Let's get the
You're
actual.
gonna get 4 sine squared u cosine v.
Okay, slow down. 4 sine squared u
Cosine v,
cosine v.
comma, 4 sine squared u, sine v, comma, 4 sine u cosine u.
Thank you.
Welcome.
Okay, so that is the normal vector for the surface. So now let's talk about the evaluation of the double integral. So the double integral says curl of f dotted with n ds on the surface, which I believe uses an s. Okay, so when we evaluate this, in the past, when we were integrating a vector field, and we wanted to dot, we just dotted the r prime with it. So now, instead of the r prime, we're going to dot the n with it. All right, so dot those two together. So we're going to take that. We have to take it with, we've got the normal for our, surface. We've got the, where's the curl?
Up there.
Oh, curl's right there. Thank you. Yeah, let me write that that's actually curl. Curl f. All right, so we'll dot the two together, curl f in this. And we end up with, when we multiply those two together, we get 4 sine squared u cosine of v minus 4 sine u cosine u. And then our limits of integration, I'm forgetting, where u was the 0 to 2 pi, right? Oh, where's our parameterization of our, oh, we never actually wrote them down. Okay, so u is the circle, so u goes 0 to 2 pi. And where does v go?
0 to 2.
We're dealing with the entire sphere, correct?
0 to 2. 0 to pi.
0 to pi. So it's the same as it would be if we were in spherical coordinate system. So in the spherical coordinate system, theta goes 0 to 2 pi and phi goes 0 to pi. In this
Wouldn't it
place,
be-
didn't we let v be phi? V is phi, and u is theta. So u is going to go 0 to 2 pi, and v will go 0 to pi. And this is a rectangle, so we're going to do du dv. Does not matter which one we do first. V is going to go 0 to pi and 0 to 2 pi. All right. Question?
Why is it high for the phi? Is it just because like we don't have a cone sort of situation?
So we have an entire sphere.
Okay, so we're not just going from here to here. We're
Right.
going from here to here.
Yes,
Okay.
exactly. So for the entire sphere, theta takes us all the way around, and if we're going to come from the North Pole to get to the bottom, we go pi units.
We're just used to doing cones with spherical.
Yeah. So that's a little different where we have to stop somewhere.
Yeah.
So if we're going to do the whole sphere, we don't stop, and phi goes 0 to pi. All the way down.
But this is half of a sphere, so shouldn't it be?
Oh, is it half a sphere?
Yeah, so shouldn't it
Oh,
be?
I'm sorry.
0 to 2
That's what I asked. I said, is it the whole sphere? And somebody said yes, and I believed you. Sorry,
So you go
my
0 to
bad.
5 or 2?
So it should go to
0
pi over 2. Yeah, thank you. Pi over 2. I didn't realize that was just a tired
Did
nod.
you see me just go?
That was a yes nod. Is it the whole sphere?
Trying to find where I
A bobbing nod.
do that over.
A nodding nod.
No, it doesn't sound like a word anymore.
It's not. How do you spell it?
N-O-D. Right?
Maybe. Okay, this is a pretty easy integral. We'd use some sort of substitution, maybe not U substitution, but you know how to integrate this one. Right? This you power reduce it, power reduce the sine part. Here you would let U be sine U, use a different U. So pretty easy to integrate, and you can confirm on your own that you get -4 pi.
So that's what that squared off answer meant. I was about to ask that. I think it's because we've been on this problem for so long.
I'm really
lost sight.
confused. Like, what are we
So-
doing?
So what was the goal?
What did we just do?
Stokes Theorem has two sides. One side is the line integral side.
It's like Green's.
It's Green's theorem with a boost. So there's a line integral side and a double integral side. The double integral side is now called the surface integral. So up here we did the line integral side. So we parameterized the boundary curve, took its derivative, did the regular line integral side. Now the double integral side, like Green's theorem, it's the double integral and we have to do the normal component of the curl. And so that's what we were doing. We were doing the double integral side. So it's
And
the
that
circulation
finds-
form of Green's theorem.
Is there one that's generally simpler than the other?
Sometimes it depends. Sometimes the line integral is easier, and sometimes the double integral is easier.
Okay.
It
It's
really,
kinda like integration, vertical and horizontal kind of thing. Sometimes it's this way, sometimes it's that way.
yeah,
Okay.
yeah. And usually, if they say to do it one way, it's because that way's easier. Usually.
Unless it's math lab. then it's just
Unless it's my
one-
math lab.
Unless it hates you.
Okay, let's talk about this one for a minute and see if we can conceptualize what's going on. Vector field. Here we have a plane that lies in the cylinder. So we've got a tilted plane in a cylinder. Cylinder is opening up, right circular cylinder. We've got this tilted plane. So we're ending up with a surface that's a tilted ellipse. It's going to be something like that. All right, because we've got a tilted plane that's passing through the cylinder. So the boundary is going to be an ellipse that's coming from that right circular cylinder. So that's going to be our surface. That's our surface. Okay. Let's look at the line integral piece first. Let's parameterize that curve. So this curve, we just have to make sure that we get the right direction for the Stokes theorem. If we look down, counterclockwise would be the way I drew the orientation. So parameterization for that curve. Parameterization for this curve. This is a curve in three-dimensional space. Any ideas?
You might be able to use polar coordinates. R squared equals 16.
So right, this is what x and y are going to be related by. Correct? Because the x, if that tilted ellipse presses down, it projects down onto a circle of radius 4. So x and y are on a circle of radius 4, but z is then?
6 minus 4 is sine 2.
Yeah, exactly. Z is 6 minus 4 sine of t. So if you were up looking down from the North Pole, you would see a circle right there of radius 4, centered at the origin. But then we add a z component that brings the z values up. So that's our parameterization. So r prime of this, pretty easy. And the direct line integral, we're going to take our function, our field, and we have to take our parameterization, plug them in, dot it with r prime, and then integrate from 0 to 2 pi. Let's stop here. I'll just finish writing up this solution as we adjourn. And then I'll put it in the notes. So that we have that one complete. We have one less problem to do on Monday. Not Wednesday. Monday. Today's Wednesday.
That's fine.
Right?
Thank you,
Yeah.
thank you.
Yeah.
I'm gonna do my master's degree on that.
Sometimes, yeah. Sometimes you just draw that perfect integral.
Why
symbol.
is this pie so nice?
I'm already like,
Yes, it does look like it's
where's Rachel?
Everyone was like, you're gonna feel like you know, you could be so long with pie. I wasn't sure you get the one
Yeah, that
a
looks
little
like it's
longer
not
than the
correct.
other because it's perfect for LED.
Young lady?
Do I not
That's
get
one way
anything
of
back
talking
for
about
12?
With the little like lightning dials
Yeah,
that
you do.
are on breadboard.
Well,
If you ever
we
notice,
drawn
there's
with
one
that graph,
that's
so I got
a
minus
little
2
longer.
there because there's no check mark.
The ones where I have
Oh,
five.
did I? Oh, I might not have seen that you changed something at 12.
It's usually so you know, but not really. But yeah, now you gotta do a lightning dial with pie.
I don't know why I think you.
Okay, I should do this.
That's
And
it.
then- Or, yeah, and then I have to have a bad one, like,
Let's take
lightning
a
pie.
look. Oh, yeah. Yeah,
That'd be great. That'd
I
be
missed
great.
it.
We'll declare bankruptcy within 3 years.
89,000.
I'll fix it in a minute.
I'm pretty sure
But
that's
you always
fan
have
mail.
little pie day specials.
Fan mail.
Oh, yeah.
That's a good
Drop
observation.
85 pounds in
That pushes you
I
into the right zone.
Into your beat.
Into the right zone. All right, let's take derivatives here, man. There's nothing left to do but differentiate. We're going to differentiate this to get R
My stuff
prime.
gets sad. No, I got really
Hey,
hot,
Haley.
so I took off my jacket.
Alright, I'm hearing stuff.
Who's talking to you?
So do you have to talk?
Nobody, I didn't sleep last night.
You have to talk to the board so that.
Talking to the board.
Yep.
It's my other me talking to me. That's
Talking
usually
to
how it
me.
goes.
Who's talking to
I
who?
feel like really weird when I don't
Minus Z and minus X, so we have to combine those things together.
Which is just say.
So it's X plus Z times minus 1, so minus 6, do you think? Do you agree with minus 6?
Yeah.
And then Y minus X is going to be 4 sine T minus 4
There we go. I got it.
Yeah, your back cracked.
Yeah. Oh.
All right, so then integral T is going to go 0 to 2 pi. And then we dot those two together, F and R prime. So we get 16 sine squared
Not wrong.
plus negative 24 cosine of T plus
I love like the
16 cosine squared minus 16 sine T cosine T
Oh, dude, yeah, right, if you do my.
dt. Cool. We're getting there.
There's a 16.
Those guys turn into a 16. And when we integrate, we're going to get 16t. So that takes care of that and that. Integrate that one, and we get negative 24 sine of t. Integrate this one, and we get negative 16 sine squared of t over 2. Hopefully you agree. Do you agree? You agree?
Yes. Most
Wait,
certain.
for the, did you power reduce really quickly on that one?
No, where? Which one?
The 16 cosine squared?
Nope.
Am I on the wrong one here?
Well, these two, when we add together, we get just 16 because it's a circle.
Gotcha.
This one, we're going to let u be sine of t, so then du is cosine t, so it's just u squared over 2.
Okay.
Of just homework?
And then that one goes away for, that one goes away.
Yeah.
So we end
I
up
have a
with
whole one notebook,
32.
homework in there from 11 to 12, and then this is 13, and I like that.
So that's the
This-
line
this
integral
class has
method.
killed several of my notebooks.
You're good.
We'll do the double integral method for this one
Your class is a
On-
notebook killer.
Monday. I know.
I have a whole
It's very
notebook.
sad.
Look,
Feel
this
bad for
one's
the notebooks.
this one's chapters 11 and 12,
Poor notebooks.
and then this one's gonna be
All right, let me
13 and
save
14.
these
I
notes.
know, I have